Thank you, everyone. And thank you for coming to my talk. And today I'm going to talk about building real-time streaming pipelines with Kafka Connect and Spark Streaming. So a little bit of spoiler alert first. So if you have been in the Spark Summit East this February, you may find this title a little bit familiar. In fact, actually, my colleague Yuan has given with the same title in February. But with some content overlaps, I'm still actually saying that given 3 or 4 months have passed, a lot of things have been updated. So if you already listened to Yuan in February, I will assure you won't regret staying in my session. So a little bit about myself. I'm an engineer at Confluent, leading the streaming processing team. And I'm also a Kafka committer and PMC member. And before that, I was in the streaming infrastructure team at LinkedIn working on Kafka and Samza. Both are the backbone streaming infra at LinkedIn. OK, so I will start with the first question, which is, what do you really need to build a streaming processing pipeline, right? And if you have been sitting in the previous 2 talks, the answer is very obvious, which is Spark Streaming, right? You have your Spark Streaming set up and done. You are good to go. It gives you very nice high-level DSLs to specify your computational logic. And it does all the legworks for handling the data parallelism, such as partitioning, fault tolerance, etc. And also, it works with a bunch of the data systems that you can read and write data from. But if you squint at this picture a little bit, you may quickly find that your data system that your streaming data sitting may actually not be showed up here in the sources and the things. For example, if you want to join like 2 streams using Spark Streaming, one of the streams may actually be produced by your web apps to Kafka, but another stream is actually some evolving logs, or it actually will be some data capture transactions from your databases, like what Jingwei has talked about in the previous Airbnb talk. And also, when you write your end results, you may not want to write it into, say, HDFS or databases. But instead, you may want to actually write it into Elasticsearch or Lucene if you're actually building a real-time indexing platform, right? And actually, more generally, when we enter the one-size-not-fitting-all era, you will find that actually there have been a lot of different data stores you can actually fit your streaming data. For example, you will have some document store, like a NoSQL store, key value stores, and also column stores. And as we also see the rise of secondary data stores, like the GraphDBs for handling your graphic queries, or temporal DBs handling your time series queries. We have also seen, like I have mentioned, the Elasticsearch, which you have efficient query processing for your text search. We have all those data that actually your streaming data can actually comes from and goes to. So, and also in practice, your company may actually not choosing just 1 or 2 of those systems, but you actually will have a mixture of a bunch of them. For example, you may have some data stores acting as your source of truth. And you have some key value stores acting as your online caches. And also, you will have some offline data stores or have some other analytics stores handling query processing functionalities. So before you actually set up your streaming engine, like Spark Streaming, into this picture, you actually need to solve a first problem, which is really to pipe your motion data from different data sources to the right place for data processing. And when we talk about the readiness of the data, another big issue to consider is basically the data format from your different sources. For example, if you want to really change just adding 1 column of one of your relational databases, it actually may have an impact in your downstream systems connected by your streaming processing frameworks, even though such of the correlation may be hard to discover because they are not directly connected. You still need to handle those schema changing issues, etc., for your data integration pipeline. And this is a real problem that we have seen in a lot of the companies, which is the real-time data integration problem. This is definitely not a new problem. We have seen it in the offline batching world already. And similarly, we have one conclusion we can make is that this data integration problem actually happens even before any of your sparse streaming job can ever happen, because you need to make sure that those data in motion are continuously piped to the right places for computation with a low latency and with a large throughput. And when we better want to have it done with a lower operational cost and the complexity as well. So what we can do with it? Well, there are several common patterns that we have seen. One common pattern is that you build like one tool for each of those source and sink systems. You want to pipe your data into your streaming engine, right? And examples include like you can use some JDBC RDD that is given in Spark. And also, we have seen some tools like Cassandra Spark connectors. And like in the previous talk, you also seen people building tools for like piping data from Spark to HBase. Or you use some other tools for piping your data to Kafka first, like Spano, like Jinwei has mentioned. And you use that to pipe into your pipeline. It will be like the very simple approach to adopt if you have one or two data systems, because you just build one tool for each one of your system. But let's say if you have N of such systems, the bad thing is that you basically have to develop and maintain N square of such sources and sinks in order to achieve such goals. So in terms of like the operational complexity, it may not be the perfect solution for you. If you really have like a bunch of different systems, you actually have your streaming data sitting. Another option that we have seen, which is kind of like the other extreme in the spectrum, is that you can build like one generic tools which works for all the systems, right? We don't see much of the examples, but in some enterprise applications, you can have some generic data copying tool where it actually makes very few assumptions about the target system because it has to be very generic. And it actually does a little bit of everything for the E, the T, and the L. And again, the problem with this option is that because of its generality, it cannot actually reason about any like guarantees or semantics of your target systems, and cannot actually provide like a very strong delivery guarantees like exactly once, even if actually the target system do have those advantages. And another option that we have seen, which is also very common today, is that you just use like a sparse streaming or Sporm or Samza or Flink to do the data copying, right? So this is something people call like using streaming tools for your copying data. And again, because we know that system like sparse streaming is good for doing the T, we just use it for doing the E and L as well. It will be a little bit overkill, actually, to use those systems with the similar reasons as I mentioned with the previous option. And you have to set up such clusters doing the data copying. And also the APIs it provides, like the receiver API, may actually be also very generic for a bunch of variety of systems as well. So what we believe that actually a better approach in between the very generic tools or using a streaming platform versus the other ad hoc one tool for each data systems is actually to think of this real-time data integration problem not as a tooling problem, but as a data infrastructure problem. And the main idea is that we can separate the E and T and L. And I'm going to talk about like one example. And since I'm a Kafka guy, I will focus on the Kafka systems today. So I will briefly talk a little bit about Kafka. Kafka is used as like a central hub of streaming data, which was originally developed at LinkedIn. The design goal is that all kinds of online systems can pipe their data into Kafka, and then those data will be available for real-time subscriptions for a bunch of other systems, as well as the offline query systems as well. So just to give you a very quick example of like the LinkedIn usage of Kafka. So this is like the pipelines we built back in 2010, where we have a bunch of sources that are generating real-time data, and we have a bunch of products that actually consume those real-time data for, say, recommendations, searches, or some online data mining and machine learning applications. And back in 2010, we do exactly the option that we mentioned in the previous slide, where we built like one of tools for each pair of the source and sink for those data integrations. So, right, so for example, sometimes we use ActiveMQ, sometimes we use a very simple Python-written log stash or log tailing system. Sometimes we use other in-house building system, as long as it works between the teams who generates the data and who consumes the data. But again, this actually will give you a very high operational cost, because you basically need to have one team developing and maintaining those links for each pair of your sources and sinks. And this is the current status of LinkedIn with Kafka in place, where we now I think since 2012, where we already developed Kafka at LinkedIn, or the data producers will actually publish their data to Kafka, which is then immediately available for online subscription for different online as well as offline system as well. So you can see here, so Kafka actually serves as like the centralized pipeline backbones for all your streaming data as well. And at its core, Kafka achieves data parallelisms by actually partitioning your data into different shards, or what we call partitions. Producers can actually publish to multiple topics, and with each topics, we have multiple partitions, which can then be hosted on different brokers or machines. When consumers consume those topics, they also actually consume at the granularity of a topic partition as well. So if you have like more than one consumers for your application, each consumer will get a non-overlapping subset of partitions to consume from. When you want to scale your data traffic with the streaming data in Kafka, all you need to do is to just add more partitions into the topics and scale your producer and consumer clients so that they can have perfect data parallelism horizontally. So back to this diagram. Given all those properties, I think it's easy to see that Kafka can fit as a central role for your streaming pipe, for your real data as well. And you can just adjust your streaming processing applications built around your Kafka clusters as like a storage layer. And for those applications such as the real-time analytics, the real-time monitoring, and also like real-time machine learning applications. But even with the current low-level clients like Kafka producer and consumers, we are still leaving a little bit on the table, which is that for each of those links, people still need to build some common tools to read and write their data into Kafka using the underlying producer and consumer clients. And things like managing those producer and the consumer clients, and as well as reasoning about metadata and doing parallelism for processing and fetching as well. The good news, though, is that instead of having end-to-end pipelines, now with Kafka in place, you always know that one side of your data integration is always Kafka, which actually gives you a better advantage of actually realizing the features and the semantics that Kafka system provides you to have like a centralized framework to doing those data integrations into Kafka. So now I'd like to talk about Kafka Connect, which is a centralized framework that is going to dramatically simplify the construction, the maintenance, and the monitoring of those data connect pipelines people build with Kafka. It is open source with Apache Kafka, and it is also aligned with the releases of Kafka as well. So it's not a separate project. And more specifically, it's a framework for building connectors between other systems and Kafka, with those associated runtime to execute those connectors in a distributed fault tolerance manner with high scale. So before I move into the details of Kafka Connect, I want to highlight some of the design goals that we make Kafka Connect. The first one is focus. we only focus on copying data between Kafka and other systems to make them to be available for real-time subscription and processing as soon as possible. And also, we actually have all the common stuff maintained in the infrastructure itself, such as the connector management, the monitoring, and the maintenance of different connectors within your single cluster. So that is basically what we call it, the batteries included here. And also, we have standardized configs as well as metric reporters inside Kafka Connect, so that let's say if you want to build a web UI monitoring all your connectors from, say, HBase, Cassandra, from your Logstash, from different systems into Kafka, you only need to build one because Kafka Connect gives you this standardized configuration as well as monitoring as metrics tools to do that. And then lastly, we want to achieve parallelism at scale, which means that users only need to develop once with like a standalone mode to deploy their Kafka connectors, which can then be automatically transformed into a distributed manner that usually you will do in production. And I will talk a little bit more with that regards. So at its core, Kafka Connect is actually very simple, right? We define two types of connect. One is called source connect, which basically you will pipe data from other systems into Kafka. And another type of connectors is called sync connectors, where you basically pipe data from Kafka into other systems. Here I show you two examples, one for the database source connector, where let's say if you have, say, a MySQL database, you have data capture logs, which captures your transactions or updates or inserts in your database. You can actually model them as streams into Kafka, where the offsets here are actually kind of like the timestamps of your updates or of your inserts. And again, this is actually aligned with the previous talk about Airbnb, where they also use sort of like the timestamps as offsets for ordering those changes into Kafka. And also, we have examples here like the HDFS sync connector, where you can use Kafka, again, to pipe the stream data into a rolling HDFS directory. And again, here, the offset is naturally just the offset of Kafka brokers, and it also gives you the ordering guarantee within the Kafka partition as well. So I want to briefly talk a little bit about the data model that we actually let users to specify code when they code with Kafka Connect. If you are already using Kafka for piping your data into, say, Spark streaming, then this data model should be not very surprising to you. Basically, for each of the continuous and unbounded data set that we want to actually pipe into Kafka for processing, we will basically define them as an endless stream. And each stream can then be partitioned into multiple partitions, where the messages within each partition will have an offset, which is strictly incrementing within the partition. And just as a concrete example, for example, the database binlog Kafka source data, you can think about your whole database as a single stream into Kafka, where each table here then will be naturally as a partition of this stream. And then the offsets of those within those tables can be treated as, for example, the row ID of your updates, or like the transaction ID of your updates or inserts as well. And since those IDs will be ever incrementing, they actually also fit in the requirement of having ordering within a single partition based on your offsets. And when we actually execute the coded connector with Kafka Connect, we actually define this single unit of processing called a task, which will have assigned one or multiple of those stream partitions to pipe between other systems and to Kafka or vice versa. And each of those tasks is basically like the smallest unit of processing, and they can be assigned to one thread. But one thread actually can also handle one or more of those tasks. Again, here, the threads also can be defined by the user when they build their Kafka Connect jobs and submit them to Kafka. I will talk about that later also. Okay, so with the data model and the parallelism model with Kafka Connect threads and as well as tasks, I will now talk about two different modes for executing the Kafka Connect jobs. The first mode is the so-called standalone mode, where let's say if you have already a coded Kafka Connect program, you can actually install that or execute that program in each one of your machines that host the source or sink of your systems. Then those different instances of the Kafka Connect will be executed independently to pipe data from those systems into Kafka and in a non-interleaving manner. So this is actually similar to Logstash or Flume, if you are familiar with their execution model. And also commonly referred as like the agent mode in those systems as well. And another manner that you can actually execute Kafka Connect is in this distributed execution. So in a summary, we basically allow you to actually set up a cluster which running the Kafka Connect runtime. And any machines in this cluster where you basically install and execute the Kafka Connect runtime will basically consider as part of this connector. But again, the Kafka Connect framework itself is agnostic to any of the resource management tools you are using, being it like Mesos or Yarn or like Docker. It actually do not care what actually runs underneath. All it needs is that as long as you have some manners to basically boot up one node which runs the Kafka Connect runtime, that is all. So in that sense, you can also co-locate your Kafka Connect programs with your Spark worker nodes or Spark streaming as well. And Kafka Connect in the distributed mode provides you this REST API where you can submit your written Kafka Connect jobs via the REST API. Then it will be basically maintained as a connector master node that actually can control multiple tasks within this connector job. And again, if you are familiar with the Spark architecture, this will be very similar to that, where you can have like the connector A and B here are the connector jobs that you submitted through this Kafka Connect cluster. And each of these Connect A or B different jobs can spawn multiple tasks that is running at the same worker node or on different worker nodes. This is actually controlled by the Kafka Connect frameworks doing to achieve a rebalance. And also we have the fault tolerance which reuse the Kafka consumer management protocol. For example, let's say if one of the worker dies, which hosts like the task C of a connector, it will be actually detected by the Kafka brokers itself and notify the Kafka Connect runtime to basically say that, okay, now you need to rebalance some of the work or migrate the failed tasks into your alive worker nodes. And the Kafka Connect runtime will automatically does the remigration of those tasks from one of those worker nodes into other worker nodes. And that I will take some more time to talk about the delivery guarantees. So as we mentioned in Kafka Connect, users have to define these offsets for their source and sink tasks. Kafka Connect runtime is actually be able to periodically commit those offsets while they are copying data between Kafka and other systems. But the user can also explicitly call commit to commit those offsets. And upon restarting some predefined Kafka Connect jobs, those offsets, which is actually stored inside Kafka as a special topic, will be fetched and reprocessed to resume the copying of the data from those positions. And because of this offset committing and resuming, for the default delivery guarantees, it gives you at least once semantics. But for those different systems like HDFS, where you can actually do better than exactly once by not using this offset storing inside Kafka, but store that with your HDFS files, we can actually also achieve exactly once for those different systems as well. And then lastly, about the serialization. Kafka Connect provides those format converters, which allows you to specify like different schema systems like JSON or Avro or Thrift. And those different schemas actually can work across different connectors. So when you actually use one connector, you can actually switch from different data formats without actually changing the code of the connect itself, but only changing a config. And more specifically, this is like the core APIs of the connector framework, where on the left-hand side, which defines a connector job, you basically can specify what the logics you want to specify for starting and stopping a connector job. And also, you specify the task instantiation, where the connector job will basically deploy across different worker nodes. And given the maximum number of tasks, you can also return a map of the configs for different tasks, which also works as a manner of creating the tasks from a given connector job. And within a source or sink task, similarly, you specify the logic of starting and stop a task itself. And for the source task, you provide a function by pulling the data into Kafka, where basically whenever it was triggered by the framework, it is supposed to retrieve some of the records in the source from the source. And similarly, for your sink task, you have these put APIs you can instantiate to have one record which is fetched from Kafka and put it into your destination system. And lastly, users can explicitly commit the current offsets when they are copying during the lifetime of your connectors. So what that gives the Kafka Connect to the Spark streaming? Well, we believe that if Kafka Connect can help you to use the Kafka systems as like the centralized hub storage layer for your streaming data, then we can actually have the separation of the E, the L, and the T, where basically Kafka Connect can be used to load data from different source systems into Kafka, and then Spark streaming then can be applied to do all kinds of transformations to build your online streaming applications. And at the end result can be pushed again from Kafka to other online or offline systems, again using Kafka Connect, which gives you this good pattern of the E and the T and the L, or E and L and T. And by doing this, we believe that we can actually lower the friction of people using different systems to host their streaming data with Spark streaming, so that the operational cost as well as the development cost can be reduced for people using Spark streaming for their applications. Okay, so lastly, I want to briefly talk about the Kafka Connect Today, which is the newest release of 0.10 in Kafka. So the Kafka Connect is only a framework, but we have a bunch of open source contributions from Confluent as well as other companies already for the past 6 months since it was released. You can see actually a list of all the connectors from different contributors in this connector hub. And just give you a quick example, we have like a Kafka hackathon in one of our Kafka our Kafka summit a couple of months ago, and some guy actually implement a Jenkins Kafka connector within a couple of hours to have it be done and deployed through the Kafka Connect. And also in the 0.10 release, we have also several improvements, such as the improved connector control for users who submit multiple connectors for different source and sink jobs into the centralized hub, which users can have a better monitoring as well as management of those different connector jobs. Okay, with that, I would like to conclude my talk. If you want to try out Kafka Connect, I would encourage you to download it from the Confluent webpage, and as well as the Apache Kafka open source webpage as well. And another reminder is that this afternoon in the downstairs, we have a book signing from our co-founder, Jay, who will be also there for answer any question you have about Kafka. Thank you.
Awesome. Let's give him a big hand.